Okay, everyone, welcome back. Hope you had a good Labor Day weekend. I did send out an email about our last class. My audio didn't record on the last class, and so if you see this, is it flashing or just it's if the white light up here is not flashing or this green thing's not flashing, then I'm not recording audio. So just like stop me or something if you see that. Um, Also, I have changed a little bit of the way I'm doing my office hours. Normally at my office hours, you just walk in and come in and see me during the time that I'm supposed to be there. But I'm trying something a little new where you can make reservations, and you can say there's time slots that you can reserve where it'll be one-on-one, where we can sit down for 30-minute time increments, and it's just you and me, and so you get that attention that you might need, okay? But you have to go do that. I sent an email out, shows you how to do it. And you can only reserve one time slot at a time. So no one can just go in and like book up the rest of the semester to make it fair so you don't have to worry about, oh, okay, these students are just filling up everything. I can never go see them. So just go on in there and make a reservation. Come in and see me. What else? I have your quizzes from last time. I will pass those back at some point in time. Actually, now's as good as any. Is it Jean Lou Sanchez? Oh yeah, Jean-Luc. Okay. Mark V. You got my email?
Yeah.
Okay. Brooke. Yes. I have a note here for you to see me. I think. Are you in the roster? Are you on the roster? Are you in the class still through? Let me see what I have here. Why did I say see me? I need to double check, but I think you didn't appear on my roster. Yeah. Okay, Rodrigo, if you could come grab these as I call you, because it'll go a little faster that way. Kara Shelton, Sean LeGros, uh, Tamikis Jackson, Anthony, is it Tem? Tem? Shokun? I'm not even going to try it. Lily, Jorge, Alexis, Paul, LaRue, right? Tyler, Mark Pena, Ruben Rodriguez. Same thing. I think I don't know if you were in my roster or not. So I'll check after class. Just remember to hang out, okay? Ernest, Elizabeth, Leon, Kyle. Oh, I know what it is. You didn't do the syllabus. I understand the requirements of the course quiz. Okay, I'll have to double check to see maybe it has been done now. Yeah, now it's locked you out, so I need to reopen that for you, but talk to me after class, that way I can do it. Honor, Williams, Aaron, Kevin. Okay. How do you say your name? Me. Okay, so I was trying to Mikas, but Tamikas. Okay. Who did I miss anybody? All right, so I did already collect the bonus question if you did the bonus question. So now it's now or never. On bonus questions, on take-home quizzes, things like that, I do expect for them to be turned in at the beginning of class. So if I have a bonus question that's due at 1 o'clock and you walk in at 1:15, I'm not going to accept it unless you've taken a picture of it with your phone sometime before 1 p.m. that shows that you had it done, okay? Just in fairness to everyone. I don't want to give anyone extra time. That's not fair, right? All right. We'll start with questions on homework or anything that you want to address. And then I'm going to get into the next section. So difference quotient. Any questions on the difference? I asked you to look at 2 questions for difference quotient. I said you might run into some issues with it. So anyone run into any issues? I did give you them, right? 1 over x squared, and then the other one was 1 over the square root of x, or just square root of x? 1 over x squared and just square root of x? Well, I tell you what, we'll do something. Would you like me to work either one of those? Which one? Both? Okay, so I gave you f of x, 1 over x squared, and I said find the difference quotient. The difference quotient, which we all remember the difference quotient now, right? There's 2 different versions. F of a plus h minus f of a all over h. And the other one was f of x minus f of a all over x minus a. What would have happened if I would have walked in today and I said, clear everything off your desk, we're going to take a quiz, write the 2 versions of the difference quotient? How would that have gone for you today? Horrible? Good thing I didn't do that. But I would expect that at this point, that you would know those formulas. So did I tell you which one to use, or a plus h? Okay, let's go with the a plus h on this one. So to do this, remember there's 3 parts to it. It's the top left part, the top right part, and then the bottom. Right? Those are the 3 things that I need to be able to figure out. The h is always going to be easy because h is always h. The f of a is relatively easy because all you have to do is replace your x here with a, right? The f of a plus h is a little complicated because you have to replace x with a plus h. So let me write it all out. I'm going to try and write it all in one line. The difference quotient is equal to f of a plus h, which would be 1 over what? A plus h squared, minus f of a, which would be 1 over a squared, all over the whole thing over h. Okay, is everyone comfortable with that as being the difference quotient? Now I need to simplify it. I need to do some algebra to get things to clean up. And I said that if you do it right, at some point in the very end, you should get the h on the bottom to cancel out. It should go away. So we have what's called a complex fraction here, right? Fractions with fractions, fractions within a fraction. So what we'll do is we'll try and combine this together by getting a common denominator. So to get a common denominator between these 2, bless you, again, what I will do is I will introduce on this fraction on the left an a squared here, and that means I have to do an a squared on top. And then on this fraction, what should I introduce on the top and bottom? A plus h quantity squared, and then on the top there, a plus h quantity squared again. You do not have to expand this. You could leave. Now you could expand it, but then your things are going to look a little different. But at the end, you should get the same result. So have to, no. Can you? Yes. All right, here we go. On the top left, when I multiply the a squared times the 1, I just get a squared, right? And then my denominator will be the new denominator, right? A squared, a plus h squared. Then minus, now on the top right, 1 times this, again, gives me just a plus h squared over my common denominator. a squared times a plus h squared. Kind of didn't need that step, but I'm showing it. So I really didn't do any algebra there, right? I mean, just put 1 times this, 1 times that. But now I can put these together, right? Because they have the same denominator. So to put them together, I'm going to put this minus this. And since I rewrote it, I may as well take the moment here to go ahead and expand this. If I take a plus h and I square it, that means times itself. I have to FOIL it out, don't I? And then collect like terms. So I'm not showing that, but a plus h squared are these 3 terms. And I will be subtracting those, right? I will be subtracting those 3 terms, which means this negative sign will have to distribute to each one of those terms. So my next line here will be a squared. That's this a squared. Then take away each of those terms. So minus a squared minus 2ah, and, oh, not plus, minus h squared. All of this divided by what? The common denominator, right, which is a squared, a plus h quantity squared. Now all of that divided by h. And I don't know if you notice this, but I'm keeping this division bar a little bit longer than this division bar because there is an order of operations here. Like you're supposed to do everything up here before you do this. So that's why I keep that division bar longer. It's kind of like this. Side note here. If I wrote 4 divided by 2 divided by 2, what's the answer? 1? That's not a good example. Sorry, let me do this one. Three halves? How'd you get 3 halves? 6 divided by 2 is what? 3 and then divided by 2? 3 halves, but wait a minute. Why not do it this way? Why not 2 divided by 2, which is 1, and then 6 divided by 1 is 6? Which one is it? Well, you can't tell because my writing of it sucked. I would have to make one of these lines bigger for you to know which one to do first. There you do this first, okay? So the answer to this would be 3 halves. Do y'all see the difference? If I do it this way, I'm sorry, yeah, then I would do these 2 first, which would be 1, and then divide that into 6, and that would be 6. So that the size of this division bar affects how you do things. Just side note, all right? All right, now some things happen up top, right? A squareds cancel. And so you're left with negative 2ah minus h squared all over a squared times a plus h squared all over, again, my division bar is a little longer there, h. What can I do now? Okay, so are you noticing right now that both the terms up here have h's in them? So you could factor an h out, and it'll cancel. But I like what's been suggested here. I could look at the h on the bottom as h over 1. Now, the reason I like to do it this way is because this division bar is separating this top from the bottom, right? If the top is a fraction, I could look at the bottom as a fraction also, over anything over 1, right, itself. So by doing that, what I can do is turn division into multiplication. Remember, division of 2 fractions is the same as multiplication of the reciprocal. So instead of writing that fraction divided by h over 1, I'm going to scrap the h over 1, turn it into multiplication, and flip it and make it 1 over h. That will help me see the next step, which is I'm going to factor an h out of the top left. When I do that, I'm left with negative 2a. I still have a minus h all over my LCD times my 1 over h. And now, can I cancel those h's? Yes, this h and this h will cancel. Because there's multiplication here, I can cancel the h's. And that's my final answer. Negative 2a minus h over a squared, a plus h squared. Questions? Comments? Concerns? Complaints? Let's look at the next one. The next one I gave you was square root of x. Would you mind if I did 1 over the square root of x instead? This one's harder. But you'll see, if I do this one, I think it'll make the other one a little easier, because you will have seen this. What's that? You want me to use that one instead? Sure. So let me do this one. I'm going to do this, and I'm going to use this difference quotient. Who did that? Who was that? Is that you, Tamikos? You're going to hurt yourself, man. Let it go. All right. So here comes my difference quotient. Oh, wait. You're not Tamikos. Hold on. Tamikos is over there. Huh? I don't know. I was trying to figure out who was who in this class while I was writing. Let's see. Thank you. Difference quotient. So it would be, what's f of x, top left corner? 1 over square root of x, right? Then minus, what's f of a? 1 over square root of a, and then over x minus a. We have a complex fraction. Now, in the previous one, I said we should get the h to cancel, right? In the previous problem, we said if h cancels, we've done good work. With this one, what we want is for the entire expression x minus a to cancel. We want that whole bottom to go away. But the top is a complex fraction, so what I will do is I will get a comment. Wow. I think the projector just died. Could be, not sure. No? That's weird. I'm waiting for that projector to die. I put a call into IT and they still haven't fixed it yet, so. Make sure I'm still recording here. Look good. All right, so I need a common denominator here, right? So what should I introduce over here and over here to get a common denominator? Square root of a here. Do the same thing there. Square root of x on the other one. So you might want to get into the habit of leaving yourself a little bit of room when you're writing these things. You know, don't try and cram it into a tiny little spot because you won't be able to add these things. Or you'll have to go to a new line and rewrite the whole thing. So what I should get here, when I multiply root a times 1 is just root a, and then over here 1 times root x will be root x. I'm going to subtract the 2, right? Do I have to worry about distributing this? I mean, there's only one term, right? Root x. So it's just going to be minus root x. That'll be it? Yes? So I have the root a minus the root x. What was my common denominator? Root a times root x over long division bar x minus a. Now this is the first time that we are going to see what I'm about to do, all right? If you tried this at home with the square root, you probably ran into an issue somewhere in this stage. I'm trying to get this x minus a to cancel. The problem is I do not have an x minus a on top, do I? I I have a square root of a minus a square root of x. That's not going to work. That doesn't cancel out. So I'm going to come in and do something that seems somewhat unnatural, but you'll see after I do it that good things are going to happen. Because I see square roots, and because I'm in Calculus 1, I'm going to think, as soon as I see square roots, of the conjugate. Do you all remember conjugates? The conjugate of this expression is that expression, but changing the sign between them. And what I'm going to do is I'm going to choose to multiply the whole numerator by the number 1. Isn't this 1? But I've chosen a very clever one, because when I do this and I multiply this times its conjugate, nice things will happen. Let's see what happens. All right, so I'm going to put some parentheses around this. I did parentheses around these because this is 2 terms, right? The other one is 2 terms. When we multiply 2 terms and 2 terms, we have to FOIL. On the bottom, how many terms are right here? How many terms is this? 1 term, right? Terms are separated by addition and subtraction. So this is a single term. This is 2 terms. So if I multiplied this through this, I would only need to distribute, right? Do y'all see there's no foiling there? All right, so, but I do have to handle the top. So I'm going to do that on my next line, but I'll draw some arrows so we can see what happens here. If I do root a times root a, I get what? A. I do root a times positive root x, I get positive root root x. But then I do the inside one, and what happens? I get negative root a root x. Doesn't matter what order they're in, right? Because it's multiplication. These two are the same thing, aren't they? And then I multiply the last 2 together, and I get what? Minus x, right? Minus x. All of that divided by what? These 2, right? Together? These 2 right here? Now, you can distribute that through if you like, or you can leave it. I'm just going to leave it. You'll see with practice and with time when you should or when you shouldn't distribute. All over still x minus a. You might be sitting there going, what was your name again? Tyler. Why did Tyler do this formula? I mean, because look at how ugly this is. If you did the other one, it would be just as ugly, just so you know. It's not any better or worse, all right? Any questions on where I am here? You see the cancellation? Here and here, right? That's gone. Which leaves me with a minus x on top. I've got this common denominator, root a root x, times the square root of root a plus root x, all of this over long division bar x minus a. Is that a good thing or not? It is, because these 2 now look very close to being the same thing, right? Except what? They're not the same, right? They're off, right? By how much? They're opposite. They're off by a sign, aren't they? So would this be a legitimate algebraic move? To take this up here, a minus x, and instead of writing it that way, to write it negative x minus a. Is that the same thing? Yes, right? Because if I distribute a negative through here, I get negative x, which is this. And if I distribute through, I get negative a, which is positive a. So that's just another, I'm just factoring a negative 1 out. Really? That's all I'm doing? If you want, you can put negative 1 if you don't like just negative. And now, don't these match exactly? But the negative 1's there. So it didn't just like magically, change. We had to pull the negative 1 for that to happen. I will also recognize now that x minus a on the bottom is the same as x minus a over 1. Why did I do that? So I can flip it up. Okay? So I can flip it up. I'll do all that on the next line. I have my negative 1. I have my x minus a. I have over root A, root X. I have my root A plus root X. I have now had someone come join up here, 1 over X minus A. And this factor will cancel with this factor. And we are left with our final answer. Root A, root X, parentheses, root A plus root X. I promised you algebra, right? I'm delivering on my promise. Any questions? So let me ask you, with the difference quotient, on the first version, the one that's f of a plus h minus f of a all over h, the goal is to get what? The h is to cancel, right? With the other formula, f of x minus f of a over x minus a, the goal is to get x minus a to cancel. So you might be asking us, like, when am I done, right? When you get that canceling, you're done. At this point, later on, we'll do something after that, but for now, that would be when we would box it up. Okay, good. Think it's time to move on. I don't expect you to copy this down, but just check it out real quick. If you did difference quotient on this one for homework, you should have started with that. And right now, at this point, I'm trying to get h to cancel, and I see square roots in the top. So I come in here with what? Conjugate, because I have square roots, right? So I go square root a plus h plus square root a, all over the same thing, square root a plus h plus square root of a. And when I do this, good things happen. And so I won't go through it, but I just want you to see, now that I've shown you, when you see square roots like that and you're trying to get something to cancel, you got to come in with the conjugate, or at least try that to make things happen. All right, so part of what I was wanting from you today was for you to watch the videos on limits before you came to class. I hope you did that. There it is, chapter 1. So we went through all this stuff already. Here we go. The limit of a function. So these are basically the notes I went through in my video, all right? And I showed you what it meant for a limit to exist. And for those of you who watched this, did it make sense? Do you have any questions on the basic idea behind the limit? We're okay? Yes. It makes sense, but how do you do that? How? Yeah, let me show you. This was just to get the idea down. Okay, so now what I'm going to do is start doing some examples, giving you problems and seeing if you can correlate this stuff that you saw to the problems, all right? All right, so here's my first example for limits. You need to take a moment to draw this correctly. So I'm going to draw a graph here. Look, this doesn't have to be perfect, all right? You don't have to break out your ruler or anything like that. We're going to say that this is 1, 2, 3, 4. We're going to say this is 1, 2, 3, 4. Okay. Take a minute to do your best to copy that, or not. It's up to you. I should have just printed this out and handed it out today, but oh well. Okay, someone's about to earn some bonus points. Let's see who it is. So please respond by raising your hand if you have a response for me here. I would like to know what the hell that means. Okay, that's I don't know what to do. How about I do it this way? I will just pick a random name here, okay? How about that? Paul, did you raise your hand? No. Mark Pena, did you raise your hand? Okay. Okay, find the limit going to the left of 1. Okay. What do y'all think? Anyone want to elaborate on that? Go ahead. Okay, x approaching 1 from the left. Yes, are we all on that? Who wants to add to that? Go ahead. From the right? No? Okay. I'll answer that question in a second. I'm just seeing if anyone else is going to add anything else to this. I think everyone's kind of got this idea, which is correct, that we are going to be approaching 1 from one side, either the left or the right, right? I mean, we're going to be approaching 1. But what do you mean by that? Approaching what? Like, what am I looking at? The y value. So you want me to look at the y value of that red function? And you want to imagine that I'm moving along the function, I'm approaching the x value of 1. So as I'm moving, here's my x values, I move across, I'm going higher and higher and higher until I actually get to 1. And when I actually get to 1, what happens to the graph? It drops down here, right, to this point, and then it does this. So the negative on the left, this -1 right here, or not, it's not -1, it's a negative symbol on the top left of the 1, tells you that you should be moving along this function f from the left-hand side. Now, it's left because think of the positive numbers are over here and the negative are over here, right? The little negative symbol up there means you're coming from this side, from the negative direction towards the positive numbers. So we're saying what y value, what's the value of the function as I approach from the left? So what is it here? Where am I headed as I start moving closer and closer to 1? It's getting closer to 3, right? But when I get there, when I actually get to 1, it drops down. So how can the answer be 3 if I drop down to 2? That's right, because the whole idea behind the limit is the limit is saying what's happening as you're getting close to the value of 1 from the left-hand side. It's not asking you what the value is at 1. That's the difference between calculus and algebra. In algebra, all we care about is what's happening right there. What's happening right there. Calculus, we say what happens as we're getting closer to that. What's happening is we're getting closer and closer. So this means we're approaching the function, or we're on the function. We're trying to see what is its y value approaching as we get closer to 1 from the left-hand side. In this case, the answer would be 3, right? What if I change it, and I say, what's the limit as x approaches 1? I put a little plus symbol on that 1 on the top right. Now we're coming in from the right side. So now here's 1, right? We're going to be walking on top of the red function, just walking along it, but moving from the right side to the left as we approach 1. So now where is it headed? The y value is getting closer and closer and closer to 2, right? Right, closer to 2. Who has a question on this? Anybody? It's okay to have a question. Yes. On the notes, I said what? You put a negative in front of the s of x, saying that it was approaching from the left to the right. That's how you would know it was going from the left to the right. I think s of x is after the... Or is it in the handwritten notes or on the video? I'll have to go back and look. Maybe we can look at that together. I don't want to take the time up here right now. I'll believe you, because you said you saw the same thing over there, right? Yes. It's undefined? Okay. Okay. This answer 3, I'm not saying that the function ever gets to 3. What I'm saying is that as I'm moving closer and closer to 1 from the left-hand side, as I'm moving towards the right, I'm getting closer to 3, right? Getting closer and closer and closer. Now, I never get there, but the limit doesn't care if you get there. The limit just wants to know where you headed. Could you say that I'm headed to 4? No, because my graph doesn't even get close to 4, does it? But my graph gets very close to 3. It never gets there, though. Does that make a little more sense? And then from the right-hand side with the little plus symbol here, we're coming in this way. Now, my graph is not getting close to 3, is it? But it's getting closer and closer and closer to a y value of 2. So the answer here would be 2. Then what about this? What's the limit as x approaches 1? I don't put a plus or a minus of the function. What's that limit equal to here? What is it? It does not exist. The limit does not exist. Now, why does it not exist? Because they're different answers. See, if I don't put a plus or a minus on the top right corner, that means you have to check both directions. If I put a minus, that means you only have to check from one side. If I put a plus, that means you only have to check from the other side. If I don't put a symbol on either one, that means you have to check from both. And for the limit to exist, they have to be going to the same place. In this case, from the left, it's 3. From the right, it's 2, right? Correct? So it's not the same. Therefore, we say does not exist. The limit does not exist. And instead of writing that, we write DNE instead. DNE. We're going there. We're headed there. That's coming. Yep. Oh, who said that? I'm sorry. I'm just hearing voices. I'm going to go, the next one after we do this, we're going to go to 2, and then after 2, we're going to go to 3. All right? But I'm still not done talking about what's happening at 1. What about this if I wrote, what's f of 1? That would be 2. Now I'm back in college algebra. I'm not asking you to approach anything. I'm just saying go to the value of 1. What's your function defined to be there? 2, because I have a solid dot, right? So the answer is 2. Any questions on that? All right, now let's look at 4 more limits. I'm going to put them on the bottom here in green. What's the limit as x approaches 2 from the left of f of x? So now here's 2. I'll just draw an imaginary line here. This is my x value of 2, right? There it is, right there. I would like to approach 2 from the negative side, which means I'm going to come in from this side and approach, we say, from the left. So I'm kind of trying to approach that yellow line on the red. So I move down, and where's the y value headed towards? Now it never gets there, right? It's getting closer and closer to 1. So the answer here would be 1. What's the limit as x approaches 2 from the right side of this function? So now we're headed this way. We're coming in towards that 2 from the right, and the y value is getting closer and closer to 2. Yes? So then what is the limit as x approaches 2 if I do not specify which side to come in on? It doesn't exist. That is a D, and then an N, and then an E. I had a student one time that we went the entire semester, and she came up to me and finally asked me, why do you always write 1? And I said, it's D, N, E, does not exist. So no confusion there. All right, what's f of 2? So what's happening to the function there? It's 4, right? The actual function value is way up here. So the limit from the left is different from the limit from the right, and the function's value is not even close to either one of those, right? Last one. Limit x approaches 3 from the left. What's that? So here's 3. Approach it from the left-hand side. So coming in like this. Why am I not over here coming in? Why am I not looking over here? Because x is 3, right? I need to get close to 3. So I'm looking at this part of the graph. Coming in, coming in. Where am I headed? Headed up to 3, right? Closer and closer to 3. What happens when I take my limit and I approach my x value of 3 from the right-hand side? I'm doing the same thing, right? I'm coming in this way now. I'm approaching 3. I'm still headed closer and closer to the value of 3. Right? So then what's the limit as x approaches 3 if I do not specify which side? It's 3 now. It's not does not exist. The only reason these were does not exist is because the limit from the left and the right were different. Right? Left and right were different. That means the limit does not exist. If the left and right limits are equal, then that's what we call the limit, without saying left or right. They're the same thing. So the answer here would be 3. And then what's f of 3? So you go to 3. What's the function's value there? There is no function's value there. It's got a hole there, right? So we say undefined. What we don't want to do is confuse these two the terminology here. We reserve undefined when we're talking about a function's value. If the function's not defined at this value, we say undefined. We use does not exist when we're talking about limits. Right? So what I would count off on a test if you told me right here f of 3 does not exist. I would also count off if on a test you told me that this limit was undefined. Does not exist is what we use when we're talking about limits. Undefined is what we're talking college algebra stuff. That sound fair? All right, that's our first example. We don't have questions there? All right, next example. I'm going to need to graph again, but let me write down what it is. I'm going to define a function right now. Cosine x minus 1. This is going to be a piecewise function. Cosine x and sine x. And this is if x is less than pi. This is if pi is less than or equal to x is less than 3 pi over 2. And this is if x is greater than or equal to 3 pi over 2. Find where, well, find limits shown. I'm going to put some limits up here in a second. That's what we're going to do, is we're going to try and find the limits. But we're going to first need to graph this. So we're going to start by graphing this piecewise function, and then after we graph it, we're going to come through and try and look at some limits. Sound fair? So here's how I'm going to graph this. Zoom out just a bit for a second. What I think I'll do is I'll start with the easier ones first, the sine and the cosine, and then I'll do this one. So do you know what sine x looks like? Yes, of course you do, right? You're in calculus. Sine looks like this. Starts at 0. It goes up to 1, doesn't it? So I'm going to say that's 1 right here. Goes up to 1, comes back down to 0, then to -1, then back to 0. And it does all that in 2 pi, doesn't it? So it looks like this. Now, I'm going to be able to erase this. That's why I would encourage you not to necessarily draw this. That's our sine curve, isn't it? But I only want that sine curve to exist when x is bigger than 3 pi over 2. So where is 3 pi over 2 on this thing? Halfway is pi, right? Quarter of the way is pi over 2. 3/4 of the way is 3 pi over 2. Yes? So we only want this function to exist when x is bigger than 3 pi over 2. That means to the right of this point, right? Also, I have an equal sign right here. That means that I want to be using this function when using the sine curve when I'm at 3 pi over 2. So what I'm going to do here, so I'm going to come in here with a black solid dot right there. And I'm going to continue this curve. Now I know that it keeps going this way, but I'm not really concerned about it. I'm just going to draw a little arrow. That sine curve keeps doing that this direction, right? That's what it's doing. And then I'm going to erase the rest of it because I don't need it, because that's the only part I'm interested in. Do you all kind of follow what I just did there? Now I need my cosine curve. Cosine looks like this. Starts out at 1, drops down to 0, goes to -1, then comes back up to 0, and then ends up at 1 again, right? That's what cosine looks like. But I only want that between where and where? Pi and 3 pi over 2. Notice that I have an equal on the pi, which means at pi, I will put what here? Solid dot. And then at 3 pi over 2, there's no equal, which means I need to put what at the end? An open circle here. And then I want everything cosine to be just the regular cosine between there and there. And then I'm going to erase the other part because I don't need it. You understand what I'm doing here? Yes. I went too far. Yes, I did. Thank you. That wouldn't have been a function, would it have been? I need to stop at 3 pi over 2. And then I need to draw cosine x minus 1. What does cosine x minus 1 look like? It's your cosine curve minus 1. Drop the whole thing down 1. So that curve that I just had that went like this, just move it all down 1, right? Which means it would look like this. And then it would continue over here, wouldn't it? However, I only want it between, well, x less than pi without the equal sign, right? So I should put an open circle here, and then to the left of that, like this, and it continues. I'll just draw it like that. I hope that makes sense. Where do you think I'm going to be interested in asking you limits? Where do you think I'm interested? At pi and at 3 pi over 2. And what are the things that you think I'm going to ask at 3 pi at pi? I'm going to ask the limit x approaches pi from the left, limit x approaches pi from the right, limit x approaches just pi, and I'm not going to tell you left or right. And then what's the last thing I'll ask? What is f of pi, right? And that's pretty standard with the way I ask things. I'll ask you for the left-hand limit, the right-hand limit, then just the limit, and then I'll ask you the function's value. And I'll do that for every point that I'm interested in. Now, I do need to technically write f of x in all of these, because what is it that I'm looking at the limit of? The function, right? All right. What is the limit as x approaches pi from the left-hand side? We didn't label our y-axis here, did we? This was -1, right? This was -1 right here, but we moved it down so it's -2 here, right? So as we come in on the left-hand side, we're approaching pi from the left. We are approaching -2. Everyone agree? What is the limit as I approach pi from the right-hand side? Now I'm over here, right? So I'm coming in, I'm at -1. All right. What about the limit as x approaches pi and I don't specify? D and E. All right. Left and right-hand limits are not the same. What is f of pi? -1, because I had the solid dot there. Okay. Tear out a sheet of paper, put your name on it, and do those 4 things, replacing pi with 3 pi over 2. Just give me the answers. Put your name on it. It's going to be a quiz. Limit x approaches 3 pi over 2 from the left. Limit x approaches 3 pi over 2 from the right. Limit x approaches 3 pi over 2. And then f of 3 pi over 2. You don't have to draw the graph. Just give me those 4 answers. In fact, we'll let this be A, B, C, and D. Just write A, B, C, D, and just give me the answers. Everyone follow what I'm asking for? Okay. I'll give you about 30 seconds. Trying to fit it all on the screen for you there. That's all the information you need to do it. If you have it, bring it up. I want to see how quick people are doing this. This isn't a contest to see who's the fastest, but I do need to see how quickly people are able to do it. That's right. Okay, thank you. Thank you, Paul. Thank you. Anybody else? Okay. Thank you. All right, that's, anyone else need to turn it in? That's really not because I'm trying to put like pressure on you and all of a sudden here's a quiz out of nowhere. It's really because standing up here, it's very difficult to gauge what it is that you're actually understanding and not. So when I do something like that, it's just kind of like doing a quick test to see if it's going in or not, right? So let's see, what's the answer to part A? Approaching 3 pi over 2 from the left-hand side. 0, because the y value here is the x-axis. That's 0. What's the limit as you approach 3 pi over 2 from the right side? So now you're going this way, now it's -1, right? The limit then, at going to 3 pi over 2, isn't the same from the left and right, so it does not exist. F of 3 pi over 2, you have a solid hole here, so -1. A solid hole. Solid dot is what I meant to say. It's solid here, which means that it's defined there, which means it's whatever the value is, which is -1. Okay? So 0, -1, does not exist, -1. Next item. This one's going to be a little different. Here, I'm going to give you I want us to sketch a function with these properties. Now, this means you need to draw a picture for me of a function that behaves a certain way, and here's the way I want it to behave. Everyone's picture might be a little different, but we should all have the same characteristics that I show here. First of all, I would like that when you draw this, the limit as x approaches 0 from the left of the function you draw, I'd like for that to be equal to 2. The next condition is that I would like the limit as x approaches 0 from the right side of the function to be equal to 0. The next condition is that I would like the function's value at 0 to be 3. The next condition is that I would like the limit as x approaches 2 of the function to be equal to -1. And the last condition is I would like f of 2 to be equal to 4. Where are the interesting things on this function happening? Like, where are we going to be looking? What x value? 0 and then 2, right? That's where things are going to be interesting. You can tell that from where I'm approaching, right? Approach 0, approach 0. What's happening at 0? Approach 2. What's happening at 2, right? So when I draw my graph, my sketch, I'm really only going to be looking to the right of the y-axis. I will call this 1. I will call this 2. I will call each of these 1, 2, 3. I'm going to have to go up again, 4. Let's first talk about what's happening at 0. I'm going to draw an imaginary line through x equals 0, which is the y-axis, isn't it? The first piece of information says that when I approach this value, the y-axis, from the right-hand side, not the right, the left-hand side, I should be approaching what y value? 2. So here's 2, right? I need to draw my graph so that it comes into 2, right? From the left, it's got to come into 2. How do I draw it? I could draw a straight line coming into 2. I could curve it around, squiggle it. Doesn't matter. I just need to go towards 2, don't I? So how about this? Wow. Come on. Come back. I wonder why it's doing that. Would this be okay? Yeah, it's doing some weird stuff before, but as I get closer to 0, it's approaching 2. Now, right now, I'm going to act like I don't know what's happening at 2, so I'm going to put intentionally an open hole there, okay? Does that satisfy the first condition? Yes. Now let's look at the second condition. As I approach 0 from the right-hand side, I need to be approaching 0. So that means here's the y-axis. When I come in from the right, I've got to be headed down towards 0, y value of 0. Oh, why is my phone on? Thought I turned it off. I apologize, everyone. So would this work? Would that be okay? Yes. Now, what needs to be happening at 0? Close at 3, y value of 3. So I need to come up to the 3. I need to put a solid dot up there. So we've got the open, then solid dot. That satisfies conditions A, B, and C. Yes? Now the next place I'm interested in is at 2. Notice also I did not extend this out like this. I didn't come way over here with it. Why? Because I've got to figure out what's happening at 2, don't I? So that's why I kind of stopped here between 0 and 2. Now at 2, imaginary line here, as I come in to 2, it says as I approach 2, I need to be headed towards -1. But it doesn't tell me which side, does it? Which means what? It's got to go from both sides, it's got to approach -1. Right? So by me not telling you left or right, I'm actually telling you both left and right. So you need to go to -1 on your y-axis. And I need to be approaching this. I'm going to leave it again as an open circle. I need to be approaching a y value of -1, both from the left and the right. So how about I connect it to this curve that I already had, bring it down, okay? And then coming off the right-hand side, just make it do whatever. Doesn't matter. You could have gone up with this, down with this. That function satisfies the condition. What's f of 2? What's happening at 2? It's 4. So I need to put a solid circle dot up here at 4. This function satisfies all the conditions, right? Yours might look different. Would this be an acceptable answer? Yeah? No. The green there, would that be acceptable? Sure. Same. Well, I need those dots to stay there, right? But that'd be fine. So that's why there's like infinitely many answers you could have. As long as you draw it with the proper conditions, it's correct. No questions? All right. Up to this point, everything we're doing, everything we've done has been very visual, right? Limits, visualizing what they are on a graph, giving you some limits, you drawing it. Now we get into how do we figure out where a function is headed if we don't have its graph, if all we have is the function itself. And this is where the torture kind of begins. So here's an example. Find the limit as x approaches -1 of x squared minus 2x over x squared minus x minus 2. Now I'm circling while you're writing this down, just to kind of point out some things. Okay, when someone writes something like this down, find the limit as x approaches -1, and they don't put a plus or minus on the top right side, that means they want you to come from both sides, right? They want you to look at this function, right? Here's the function. We know that that's some f. We know it has some graph. And what we're saying is if we looked at that graph and we approached one from both sides, where's it headed? But we're going to try and do this without graphing it, right? Without graphing it. So this method that I'm going to show you right now is we're going to use a table. And this isn't a very efficient method, but it's a good way to start to kind of get our heads around the idea of what we mean by approaching something. So let's start from the left side, all right? And since I'm going to start from the left side, I'm going to label this all in blue. I'm going to come in from the left. All right, so I'm going to approach x equals -1 from the left. Let's start there, then we'll come in from the right in a little while. To do this, to approach x is -1 from the left, let me draw a quick number line for you. Let me label -1 on here, and let me pick a couple of points that are to the left of -1 that sequentially get closer to -1. So what is a number to the left of -1 that I could use? And then let me answer that for you. How about this? Would -1.1 be to the left of -1? Yes? Right, because remember the way right, it's 0 to the left of that's -1, then -2, then -3. So as you move to the left, the numbers get bigger. Negative, but bigger. What would be a number even closer to -1? How about -1.01? That would be even closer. What would be another point even closer? -0.01. 1.001, right? What would be even closer? Negative 1.0001, right? And could you get closer and closer and closer? And you could do that forever for the rest of your life and die and never get there, right? I mean, you could do it forever. You can keep getting closer without actually ever getting there and never run out of numbers. So by a table, what we mean is we're kind of going to say we're going to get close, but the idea of close is very arbitrary. And you'll realize that's one of the major points in calculus. Like right now, are we close? Okay. Am I close to SeaWorld? Am I close to the sun? Okay. If I think that I'm close to the sun, then SeaWorld is extremely close, isn't it? Like, if I think I'm close to the sun, like Alpha Centauri, the next star past our sun, right, is so far away that it makes our sun look like it's really close. So I guess what I'm getting at is close is a relative word, right? Close is relative. So when we say close, if I say negative 1.001, you could turn around and say, man, that is not my idea of close. My idea of close is 1.0000000 with a million zeros, then a 1. That is close to you. And then someone comes in and says, no, a billion zeros and then a 1. That's close. So the idea of closeness is very arbitrary. And in this class, we are not going to investigate how mathematicians get around that, because we have a very formal way of doing it. And become a math major, and that's what you would investigate. But I'm not going to do it here. For us, we're just going to accept that these are getting closer and be happy with it. All right? And try and notice a pattern of what happens when we take those numbers and plug them into the function. So we're back in college algebra right now. We're just going to plug this value into the function, plug this value into the function, plug this value into the function, and try and see a pattern of where the answers are going. Make sense? Now, to do this, we're going to need a calculator. But we're going to make a t-table. It's like here's our x, here's our f of x. We're going to plug in negative 1.1, negative 1.01, and then negative 1.001. Yeah? But I've got something that's going to save us a lot of time, okay? I'm just going to use my Mathematica to do it. So the function I'm using was x squared minus 2x over x squared minus x minus 2. And I can ask Mathematica to replace x with anything I want. So how about, what was it, negative 1.1? If you do that, you should get 11. All right? You get 11. So I just plug negative 1.1 in there for us, all right? And it comes out to be 11. Now I'm going to plug in what? Negative 1.01? And I get 101. 101. Then I'm going to plug in negative 1. Where'd it go? Negative 1.001, and I get 1,001. What appears to be happening here? Yeah, but what's happening to my y values? They're getting bigger, right? They actually look like they're getting bigger really fast, and it looks like an asymptote. It looks like our function is wanting to take off towards a positive infinity, right? Let me go a little further. How about I go 1.0001? Now I'm at 10,001. So the closer I get to negative 1 from the left, the bigger it's getting, right? Now, that was what was happening when I was approaching it from the left. So I'm just going to say, these are getting closer to positive infinity. Let me continue now and come in on the other side. So I'll come in with the red, and I'm going to approach it from the right. Give me some numbers that would be coming into -1 from the right. -0.9. What's one even closer? -0.99, even closer. -0.999, right? And I could keep doing that. Get closer and closer and closer to -1 from the right. And then I make a table off of those. Now let's see what happens. I'll ask Mathematica to do it for me again. 0.9. I get -9. Where do you think this one's going to go? Think it's going to go like to -infinity? -99 is what I get when I do the next one. And then do one more, 0.999, -0.999. I get -999. Would anyone have any idea what I was talking about if I said Necron 99? No? Okay. It was a cartoon I watched when I was a kid. Let me see if I can remember. I don't even know how to spell it. Necron 99. He was a cartoon character. Yeah, he was like an assassin. Yeah, that was him. It was a cartoon I watched when I was a kid. I don't know why I just thought of that. It's weird how the brain works, right? You just like tap something from the past, just it's there. So this appears to be headed which way? Man, I really hope that's not my computer. Although it is looking like it is. I wonder if my display port on this thing is crapping out. That would be tragic. It could be this projector, because I'm not real convinced that this projector is in good shape. I'm not going to touch it. So it looks like as we come in from the left, it wants to go up forever, right? And as we come in from the right, it wants to go down forever. So what would you say is happening here then? What do you think this limit is then? It doesn't exist, right? It's not headed towards the same place? Yeah? Yes? So we would say this does not exist just from our analysis of the table. You'll be asked to do that on your homework, so I just want you to be familiar with what it is they're asking you to do. Now, just out of curiosity, what would happen if we actually plug -1 into the function? Like if I ask you, what is f of -1? It's undefined. Why? You'll get division by 0 on the bottom, right? If you hadn't tried that, you can try it. You'll get division by 0. But we will get around this. How are we going to get around this? We're going to use a difference quotient. And we're going to get things to cancel, like that h or that x minus a is going to cancel, and then we're going to be able to do it. And we'll be able to figure out where these things are headed. But that's just something you're going to have to stay tuned for. All right. We have 2 more examples. How about this one? Find the limit as x approaches 0 of 9 to the x minus 5 to the x all over x. Now here's what I'd like for us to do to start to get into the habit of doing, I should say, is anytime we see a limit and it's approaching something like here, it's approaching 0, to get into the habit of just first figuring out what would happen if you tried plugging 0 in. So just plug 0 in. Let's do this on the side. What would you get? 9 to the 0 minus 5 to the 0 over 0. What's 9 to the 0? 1 minus 5 to the 0. 1, so you get 0 over 0. This is what we're going to look at from here on out and say is a very bad thing. All right? It's a bad thing. But it's actually going to be a good thing because we're going to be able to find a way around it. But what we don't want to do is ever look at 0 over 0. When we're looking at a limit, we don't ever want to look at 0 over 0 and say 1. Right? Like anything over itself is 1. And we don't want to say 0 divided by 0 is 0. And we don't want to say 0 divided by 0 is undefined. We want to say from now on, anytime we see 0 over 0, that's why I'm in calculus, is to be able to handle that. All right? But we can't just, we know right now that we can't just plug 0 in. We have to figure out what's happening from each side. So I need to make a table. And I think for this, I'm going to kind of knock these all out at one time. I'm coming from the left and the right all at the same time and make my table. So here's my table. This is going to be my x. Here's going to be my f of x. And let me see. Give me some values that are getting close to 0 from the left-hand side. 0.1, negative, 0.1, closer. Closer. I'm not too concerned because I do have a wireless display adapter that I can go wireless if I need to. But I'm concerned about this.